Okay, why don't we get started? So today we're switching gears a little bit in this course. So we're going to switch from CT and start our treatment of MRI. Before we start, are there any questions about logistics? The main thing obviously is next week is project presentations. So half the groups are going to present live on either Monday or Wednesday, and the other half you'll just submit remotely. In the past, everyone's been live, but the enrollment is basically doubled this year, so we have to sort of split it into live and remote. Okay. We'll send out an announcement with more details, but basically you should be, even if you're live, be ready to log into Zoom, because we'll use Zoom to just share your screen. That saves a lot of time. Otherwise, we spend a lot of time hooking computers up, and that just wastes a lot of time. All right. So everything's gonna be on Zoom, even if you're live. All right. So if you're live, you're just gonna come up to the podium with your group, but present on Zoom, and we'll record it. And also that's how we're going to switch talks. All right. Any questions about the projects or the current homework? Okay. So basically the current homework 4 is just 2 sort of problems. And the second one is just sort of guiding you through how to use MATLAB. So hopefully it's not too strenuous. You have 2 weeks to do that, but, schedule, make use of that scheduling. There will also be another homework posted later today, which will also be relatively light, just to sort of get you sort of, sort of geared up to sort of MRI stuff. You'll also have 2+ weeks to do that, but just sort of make use of your time wisely as well. All right. Okay, so before we begin, any questions logistics wise? Okay. Professor McVeigh, I see you're online. Anything you want to add about projects?
Nope, I don't think so, as long as everyone's busy working on them.
Okay. Great. Okay, so if you need any help, just send us email. And otherwise, we will start the lecture now. So today, we're going to cover a bunch of these things. We'll mostly spend time talking about the MRI system, getting into spin and magnetization, something called precession. We'll probably get as far as RF excitation, and then when we come back from projects, we'll probably get started on these topics. We'll see how far we get today, but there's no rush. We'll sort of just work our way through these key concepts. Okay. So most MRI systems look like this, and so the main thing is that in MRI, there's actually 3 coils you need to think about. Okay. The first one here is this magnet, and that's what makes this really heavy and expensive. This is to create a very strong magnetic field, and we'll talk about how strong that is in the later slides. Okay, so that's the main coil that makes it big and heavy and expensive. Although, as we'll see, people are working on ways to reduce the cost and size of that. The other coil we're learning about is gradient coils. Okay, so within the big magnet, there's another coil which is called the gradient coil, and sort of typically concentric. And that is going to be used to create spatial variations in the magnetic field. Okay, so the main coil creates a very uniform field, ideally. The gradient field actually imposes spatial variations in both X, Y, and Z directions, and that's what allows us to do the imaging. Right, so we'll spend quite a bit of time talking about how that works in later lectures. And then the final coil is the radio frequency coil, which sits sort of inside those other 2 coils. And that can be either big to surround the body, or it can be smaller. It could just surround the head or the knee or whatever you want to do. Okay. And that has actually 2 functions. It has both a transmit function, where it's going to put energy into the body. And it's also have a receive function, where it's going to listen to the signal from your body. Okay. Those 2 things can actually be decoupled. You could have one coil that's doing transmit and one coil that's doing receive. Okay. Or you could have one coil that does both. It can be in transmit mode and also receive mode. All right. So you can think of that as sort of the antenna of our system. All right. This is sort of a diagram of sort of what the coil looks like. So this is sort of a winding, and we use superconducting wire. So this is an example of niobium titanium filaments embedded in some copper wire here, showing a cross section of wire from a superconducting magnet. And you can see here that basically you've got the main windings here, okay? And then it's surrounded by a lot of liquid helium, okay? So the way this works is when you get your magnet, okay, they ship it and it's not at field yet. So it doesn't really have any field, okay? And then you plug it into the wall, maybe for a day or two or a week, okay? And just let it charge up. And then you unplug it. And the current just keeps going because it's superconducting wire. But you need to keep it really cold, so that's why you need the liquid helium, which is going to turn out to be a slight problem, as we'll talk about in the later slides. Okay. So one thing we need to sort of talk about a little bit is what units we're going to use. And we actually have to get used to sort of two sorts of units. There's the SI units and the CGS units, and both are used. And so you sort of, if you're NMR, you sort of have to, especially if you're in the United States, you have to sort of do both. One unit is the Tesla, okay? So named after Nikolai Tesla. That is equal, and the other unit that's used a lot is Gauss, okay? Gauss is after Carl Friedrich Gauss, you know, the Gaussian and all that stuff, okay? So two famous guys. And so 1 Tesla equals 10,000 Gauss, and so that's the conversion, all right? To give you a sense of what these field strengths are, the Earth's field is about half a Gauss. Okay, so that's useful to remember if you're trying to think about sort of how strong is a field. So the Earth's field is about half a Gauss, which is 50 microteslas. Okay, so that's sort of thing. And then and the Earth's field does vary across, the magnetic field does vary across Earth. This is probably from a while ago, but just showing you here in San Diego, we're pretty close to about 50 microtesla. Okay. Now, since I don't remember when I got this plot, but it's changed since then. As you know, the Earth's magnet is sort of flips every once in a while. So north becomes south and south becomes north. Okay. And there's a really interesting story about how, you know, the sort of the movement of the plates and the plate tectonics. Basically, a lot of the way they figured out that how those things fit together is basically because the Earth's magnetic field was flipping over time, they could sort of see when things flipped and sort of say, okay, well, this must have gone here and this must have gone there. So it is changing, but slow enough for most of over our lifetime, it's not going to change that much, but eventually it will change. Okay. And so you'll have on the homework that's posted today, you'll have an opportunity. The nice thing now is with your iPhone, you can go and measure magnetic fields. So part of homework 5 is you're going to go measure magnetic fields around campus if you want. Okay. So you get a sense of what the strength of the field is. All right. And also put it next to a magnet and just sort of go wild. Okay. All right. So let's talk a little bit about sort of what magnets we have on campus. So for example, on campus, we have this, the highest field strength we have here at UCSD is 3 Tesla. Okay. And this, we have both G and Siemens. Now, this is sort of for sort of standard for sort of premier clinical care. 3 Tesla is considered sort of the standard. I mean, there are lower fields like 1.5 Tesla, but if you look here in the hospital at UCSD, you know, so for all the high-end scans, we're going to a 3 Tesla. Okay. Now, I think either a year or two ago, 7 Tesla was just approved by the FDA for certain clinical scans. And so there's probably about 100 of these. We'll talk about that in a minute. And then there's a lot of research scanners that are 9.4 Tesla, 10.5 Tesla, 11.7 Tesla. And this one we'll talk about here in France, also 11.7 Tesla. And so one of the questions is, why do people keep building these bigger and bigger magnets? All right. And what we'll find out is the more your magnetic field strength is, the more signal you get. Okay. And so you're always looking for more signal. And so that's why you're willing to pay. And in terms of the cost, it's about a Tesla, it's about $1 million per Tesla, roughly. Okay. So if you want a 3 Tesla magnet, you need to have $3 million. If you want a 7 Tesla magnet, you need about $7 million. That's just for the magnet itself. Then you have to site the magnet, you have to build the room. That's easily another $2 to $3 million. Okay, or $1 million, depending on where you want it. We'll talk a little bit about that siting cost. So that MRI is a very expensive technology. Okay. This is just showing sort of the distribution of high field magnets around the world. And so you can sort of see this was up to 2019. There were about 100 of these 7T systems. I think the closest 7T system to us right now is at USC. So there's a few of these in the in California at least. And then if you go to like Minneapolis, they've got a 9.4 and a 10.5. And then the 11.7, at least when this was done, there were just a few of them. And then there's some planned projects at 14 Tesla. So you sort of see people, part of it is people want more signal. Part of it is just there's sort of like some, people just like to have the biggest magnet. Okay, so it's sort of a bragging right. Oops, I cancel that. Whoops, what's going on here? Okay, this is a magnet, the one in France that just came on board last year. So these are the first images of the magnet here of a, I think what is it? A pumpkin or something? I forget what it was. Let's see, why does this keep asking me to do things? Okay, and you can sort of see this magnet is huge, right? These are the people, and this is the magnet, okay? So it took a lot, and it took probably over, I forget, maybe 10 or 15 years to build this magnet, okay? I think one of the stories behind this magnet is they had a lot of, so in high energy physics, you know, with colliders, you use magnets a lot to steer the particles, and you know, like at CERN or at these, you know, any place you want to sort of do high energy particle physics. And so there's a lot of people in the world who have magnetic high field magnet expertise. And I think there were just, the story goes, there were a bunch of them in France, and they needed to give them something to do. So they figured this was a good project for them. Okay. And kept them employed for quite a long time. All right. So this is sort of more details on that magnet. You can sort of see it's a beast. It's like 132 tons. Okay. So it's not a small magnet. Okay, this is actually these are some pictures from last year. So showing you when we replaced one of our magnets, we went from a GE to a Siemens magnet here. And so what you're seeing here is you're seeing some of the helium blow off. Okay, when we decommission a magnet, we have to let the helium blow off and let the field come back. And then you need a big crane to put the magnets in. Okay, so you take one magnet out and you put the other magnet in. And luckily, we're just a one-story building, so it's sort of fairly easy, but still, the magnet is too big to go through the hallway. So you've got to sort of lower it in through the, yeah.
So as you grow up in like the Tesla now, are there any safety concerns?
Yeah, there are quite a few safety concerns, which we'll get into. One is just things, it's a magnet, so it will track things, right? And the stronger it is, the more easily it will track things that will fly into the magnet. So if you're in the magnet when something's flying in there, you're basically dead, okay? So that's not good. The other thing that's sort of cool is not so much with 3 Tesla, but when we used to have a 4 Tesla magnet here on campus, and essentially you just go towards the bore of the magnet, you just like shake your head a little bit, you'll get nauseous or dizzy, or you'll see things flashing. And what happens is if you go back to Maxwell's equations, right, dB dt gives an electric field. So if you're moving in a magnetic field and causing dB dt, you're causing electrical currents in your brain, and that can have different effects. So actually, as a field gets stronger, so like, and it's like, you know, Professor McVeigh was talking about CT, where you go zoom, right? Yeah. Well, if you do that in a high field magnet, that would cause problems, right? Because you're moving very fast in the magnetic field. You could actually trigger like stuff in the brain, or, you know, you could even, if you did fast enough and the conditions are right, you could actually trigger the heart to go into arrhythmia or something, which is not good. Okay. So yeah, basically, and we don't actually know. I mean, as people build these stronger magnets and people go into them, maybe we'll find out there's some field at which people just, their brains go weird or something. We don't know. So that's sort of, it's sort of exciting. It's sort of like you're pushing the frontier of what can happen. Okay. Yes, question. Is there any particular reason why those magnets? Yeah, there is a particular reason in terms of, you know, like for example, 7. So basically, we'll talk a little bit later about the resonant frequency. So for example, there's this thing called the lawnmower frequency. So for every Tesla, the frequency is about 42.5. And so there's a couple of things, like for example, 7 Tesla is a popular field because 7 times 42 is about 300, or was it like 7 times 4 is what, 28? Yeah. So about 300 megahertz. So there's sort of like sometimes, so historically there's been sort of this, there are certain fields that are just sort of integer, sort of 100 megahertz things. But the other thing is just how much money you have. Okay, so for example, the Minnesota 10 point, like why did they pick 10.5? Basically, that's how much money they had, right? It's like, okay, how much, we have this much money. How big of, how much wire can you give me, and what can we do? So that's why they didn't go to 11.7, right? Part of the reason. Okay, for example, there's a jump from 3 to 7 Tesla, right? Because a lot of it's just sort of trying to figure out what is going to be enough field strength and be the right cost point. But that's not to say I know there are manufacturers thinking, well, maybe we should be at 5 Tesla. Okay, so it's not always. There's some historical reasons, but there's also just people guessing at what's going to be the best field. Yes.
So if the rooms, like compared to like 3 Tesla, 6 Tesla, do you have to make the MRI room double the size? When the field comes in?
Yes and no. There's always a trade-off between, I mean, the early 7 Teslas, you basically, you have to do 2 things with magnetic rooms. One is you have to, like if we put a magnet in this room, one thing we have to do is cover it with copper shielding, right? Because we don't want like interference coming in and we'll talk about that in a minute. But the other thing we have to do is we have to make sure that, like, if someone is walking through the hallway, let's say they're running through the hallway and they happen to have a pacemaker. So usually you probably wouldn't run if you had a pacemaker, but let's assume you were running if you had a pacemaker. We want to make sure that we don't induce electric currents in their heart. So there is a limit in terms of, there's something called the 5 Gauss line, which we'll get into. And so you have to put iron around the room too, which is very expensive. So if you were to buy a 7 Tesla like 10 years ago, a lot of the cost would have just been putting iron all around this room. Okay. But now the manufacturers are coming up with better ways of sort of self-shielding the magnets so that you don't have to use so much iron. Okay. But there is a cost. And also, as these things get heavier, obviously you need to make sure, like, on the ground floor, it's not a big issue, but if you're like, 3rd story in a hospital, you may not be able to put a big magnet up there, right?
So do you just put it in normal ground floor? Or?
A lot of them are ground floor, but like even our building, when we just put in this magnet last year, it's on the ground floor, but here, I mean, a lot of UCSC is like landfill, right? So it's like 50 feet down to bedrock. So our building is actually standing on stilts. So in an earthquake, it's just going to go like this, right? Hopefully not fall off the stilts. So we're not really on the ground, right? And even if you're on the ground, if the ground is soft, you don't want the magnet sinking into the ground, right? So we had to make sure and double check the drawings and make sure that the original designers had put an 8-foot concrete slab throughout, and it was deemed sufficient to hold the magnet. But yeah, I mean, there's a lot that goes, and you can't just put a magnet anywhere if it's that heavy. Okay, anything else? Question? Yeah, so every building's different. Like in our building, we have a skylight, which we take apart. But like in this building, for example, let's say we want to put a magnet in, we probably have to tear down that wall, right? Open up, and in fact, every time we put in a magnet, we open up the walls. And so it's not an easy expense. Okay, great, good questions. All right, anything else? Okay, and so then after we put in the magnet, this is just showing you the side of the magnet. And so this is actually something that's only been happening over the last 5 or 10 years, where it used to be all the electronics was in another room. But there's advantages of putting the electronics closer to the magnet because you have less loss of signal as you're going through the cables, okay? So now a lot of the newer magnets, a lot of it, much more is we're in the room right attached to the outside of the magnet, okay? And so people have had to figure out how to make all that work within the magnetic environment. Whereas before it was thought you have to have everything outside the room, okay? This is showing like a helium dewar filling up the magnet, okay? Typically the magnets might be shipped with a little bit of helium, but then you need to sort of top it up and then start charging up the magnet. And then when you're done, you have this really nice looking magnet. Okay. Yeah, so what can go wrong? Yeah, so one thing is that you just want to make sure that you don't bring in anything ferromagnetic into the magnetic environment, because it will become magnetized and be pulled, sucked into your magnet. And so like this, when I, for example, I'm not sure, I didn't check again this year, but last year, for example, and this is very, I mean, it happens more often than you'd like. People just come into the magnet room, you know, carrying an oxygen cylinder, and the next thing you know, it's just pulled out of their hands. And these fields are so strong that I mean, if it's really in the right conditions, there's no one in this room strong enough to hold something and not have it ripped out of their hands. Okay, that's how strong these fields are. So we're not going to watch this together, but I encourage you to watch this. It's sort of a fun video. It's about 10 or 15 minutes long. So just go to this link, and it shows lots of fun things you can have by throwing things into the magnet. Okay. But the main thing I want to get, if there's the only thing you remember from this lecture or this class, is the magnet is always on. Okay. Which people don't always realize. Like they're like, well, it's not make, because sometimes magnets make sound. And we'll talk about why the MRI system makes sound. But even if it's not making any sound at all, unless you are explicitly told that the magnet is off, the field is always on, always. Okay, so so be very conscious about anytime you're doing MRI, either for research or even if you are like a patient. You know, I'm always very paranoid. I've been in a, you know, I've probably been in an MRI system 100 times or something. I don't know, maybe more, but I'm always, you typically have a mirror so you can see what's going around you. And I'm always looking and seeing who's coming in and what they're doing and making sure that they're not carrying an oxygen cylinder or something like that, or a tool. Okay, I've seen very close cases where people have almost been killed. And it's sometimes the most experienced people who just forget and bring in, like, you know, a cable, a coil. I saw one case where an engineer brought in a coil of wire, which the wire was okay because it was copper, but the spool was metal, was steel, and it was like sucked into the magnet bore. And one of my students was here and just lifted his head just as this thing went by. So that's the closest I've seen. That was, and this was like a very experienced person. So just always be, if nothing else, just remember that MRI is, there are dangers, and so just, you know, take care of yourself in the magnetic environment. Question?
So magnet is always on. Is it because the time and cost is too much turned off and on? Or?
Yes, for these big field magnets. Now we'll talk about sort of lower field, cheaper magnets where you can turn the field on and off pretty quickly. But for something like this, I mean, imagine plugging something in a wall and letting it go for like a couple days. That's a lot of power, right? I forget how many megajoules that, but it's in the slides. You can see it, you know, talking about megajoules of energy, right?
Is it expensive to have the MRI always on?
No, because once it's on, then it's just, the current's just going. So, I mean, that in itself is not expensive. Having an MRI system is expensive because things break and you have to fix them. Yeah. Okay. All right. Okay, so let's do a sort of a thought experiment. Imagine you're standing here. So I can actually draw a person here. Okay. So you're standing here and you're holding a wrench, right? Despite this lecture, you decided to enter the room with a wrench, okay? An iron wrench, right? A very heavy iron wrench. And it is sucked out of your hands into the magnet, right? Okay, so what I want you to think about is at some point this wrench has to stop, right? It can't go forever. So what point is it gonna stop? Is it gonna stop at point B, C, D, or E? Okay, so just think about that for a minute, and I guess I could do a poll on Zoom. Let's do that. And then in class, what I found to be more efficient is, so we're gonna launch the poll. So online, you can sort of pick A, B, C, or D, or E as to where the wrench is gonna stop next. In class, I'm gonna give you about 30 seconds, and then you're just going to yell out your answer, and we'll do sort of a weighted audio poll, right? Otherwise, it takes too much time to do it, right? Okay. So think about that, and feel free to talk to your neighbor. Give you about 20 seconds and think about, you're there, the wrench is pulled in, where is it going to stop first?
my guess, dude. I think it's like C or E. Like a gradient all the way across the cylinder. Or yeah, or it like goes with and I'm feeling good about C. Just like the SATs.
And Z is the.
Okay, let's just for fun, let's on the count of three, just yell out your answer. Okay, so I know it's gonna be weighted by how loud you are, but just, you know, if you feel passionate about your answer, you can yell louder. Okay. All right, 1, 2, 3.
C.
All right, good. Even online. Okay, you did the polling and the, so I think both in class and online, C is the right answer. So C got 57% of the votes online, and I think it was the loudest here. The answer is actually E. Okay, yes, question.
I'd argue it's actually none of the above.
Is it none of the above?
Mechanics, if you don't have anything stopping the wrench to make it collide, it's going to accelerate, it's going to keep flying.
Is it really? Okay. So that's a good question. So let's think about it. So first of all, there's gravity, right? So at some point it has to fall down to the ground. But let's just say things happen so fast with gravity. So if I'm holding a wrench here, it's got some potential energy, right?
Right.
At what other point does it have the same amount of potential energy? So imagine, like, let's say, you know,
Maintain the same height.
yeah. So it's like if you go back to physics, imagine there's a bowl, right? And you're here and you let go, where are you going to end up? On the other side of the bowl at the same height, right? So the ball's not going to keep going forever, right? Right. So think about potential energy. There's some potential energy, right? You're holding that, right? It required you it's requiring you some energy to hold that, right? You let go, it's going to go, assuming it happens so fast that gravity is not a factor and it's a straight line, you haven't angled it, you're right in the center of the magnet, it's going to go right from A to E. Okay. And now comes the interesting part. What's the next point it's going to stop at? It goes from A to E. What's the next stopping point? A. It's come right back at you. And it's actually going to happen before you even know it. Okay. And I've actually met people where this has happened. You know, engineers, actually very experienced engineers, where they've almost lost their hand. And the only reason they didn't lose the hand is because it didn't go straight in. Right. It was sort of because, you know, where you are, you know, it's only if you're in the center that's going to just go straight. If you're off at an angle, there's, depending on the field, it's going to sort of maybe hit the thing, ricochet around, come out here, and then come back. Okay. So anyways, so if you're working with MRI, just be very careful. It is a very dangerous thing. And luckily I've not seen anyone hurt or killed, but I've seen some close calls. Yes. Yes, if there was no gravity and it was perfect, yeah, it would just go on forever. Just like a, you know, simple harmonic oscillator with no friction. Yep. Okay. All right. So I don't want to scare you, but I do want to scare you. So it's safe. I mean, there's thousands of MRIs done or more per day, and you know, we know how. If you're, as long as you're paying attention and you're safe, it's good. But you just have to keep that in mind. So one thing we talked about is, you know, if you have a magnetic field, you don't want necessarily, you want a strong magnetic field inside the magnet, but you don't want that magnetic field to go too far outside the magnet. And we'll talk about why. And so typically most designs now have a main sort of set of wires inside, shown here in red, and then there'll be these counter windings that will create magnetic field that goes in the opposite direction. So you sort of cancel out the field outside without really perturbing the field inside. Okay. So that's what's called the self-shielded magnet. And so every magnet you get will typically will come with sort of a pattern of the field strengths. And so sort of see here, you're at, this is a 3 Tesla magnet. So in the center of the magnet, you're at 3 Tesla or 30,000 Gauss. The point that we like to be at is half a Gauss. Okay, so where is that here? Half a Gauss. This is the line sort of that sort of, according to safety regulations, you have to keep this half Gauss line within the magnet room. Okay, this half Gauss line cannot go outside. Now, the reason for that is not totally clear, and it's probably too conservative. But back when, for the older generation of pacemakers and things, the concern was if you had a person, and obviously people who come to a hospital, there's quite a few who will have pacemakers. If they walk past an MRI room and the field is too strong, it causes electrical currents in their pacemaker, which can screw up their pacemaking. So that was the main concern. So this, for example, is we were simulating what would happen if we put a new magnet in, and what we found was that the this is the room. This is where the magnet would be. This is the wall, and there's a public walkway right behind our building, which is shown here. Okay, and I think for the homework 5 as extra credit, you can actually go and measure the fields back here, okay, and verify that they're safe. But with the original thing, you see this half Gauss line was poking just a little bit into the public walkway. And so even though it's highly unlikely that someone will be walking really fast right against the wall, we still have to make sure that that doesn't happen, okay? So for example, this is just showing how little that would extend into the walkway. But still, even, if for some reason someone just decided to do that, then it could potentially be a danger. So we ended up having to move the center this way such that a half Gauss line is now contained within the room. It doesn't go into the walkway. Right? So that's sort of a practical application of what we have to do. And this is and there's actually a big metal plate back here, okay, in the wall. Otherwise, the field will go out even stronger. So this is shown by this here. Typically, a lot of MRIs are donut designs, but there are, for example, designs like sort of this pancake design or this sort of double donut design, okay? So this is, for example, useful if you want to sort of see someone as they're sitting and standing, if they have lower back pain, that's useful. This is useful for people, for example, who, get claustrophobic and may not want to go to a traditional MRI. And especially if you just want to image their hand or their leg or extremity, then something like that would be good. But those tend to be lower field. It's hard to get a high field with these designs. And so all the high field magnets tend to be the solenoidal design. As I said before, and this was just, I think, just a few days ago, this was in the news, there's a helium shortage, right? And so the idea is that these magnets use a lot of helium. And so there is a push on the MRI manufacturers. So not only is the helium expensive, but there's also a shortage, okay? And in fact, it's actually quite interesting that it's actually even affected by the war in Ukraine, as this article talks to you about, that there was like even a facility in Eastern Russia where they were hoping to get more helium now with the war. So geopolitical issues do have an effect on what happens locally. And so helium is being rationed out, okay? So that's led to manufacturers trying to come up with designs that don't use as much helium. This is from a Philips, where like a classic technology that they would have might use 1,500 liters of liquid helium, okay? And I forget the price of this, but it's helium. Liquid helium is not cheap. You're talking about hundreds of thousands of dollars sometimes to buy liquid helium, okay? To this much liquid helium, it's probably more. So this one, by contrast, uses only 7 liters. Okay, so engineers over the last decade or so have come up with ways where you can, instead of using liquid helium, they just find ways of thermally conducting heat very quickly away and dissipating the heat so quickly that they need less helium. Yes.
Is it only available in lower field, like 3 Tesla?
Yeah, 3 Tesla. I'm not aware of one that has that for human size yet. Certainly, as you go to a smaller magnet for like little animals, you can get it for at higher fields. But for something this big, I'm not aware of anything yet at 3 Tesla, although I'm sure people are working on it. This is another example. This only uses 0.7 liters, but as you can see, it's a lower field strength of 0.55 Tesla, and this is from Siemens. Okay. So there's 2 things. One is you don't need much liquid helium, and also it makes the sighting easier because typically liquid helium, you need to have a pipe so that liquid helium can sort of blow off if there's an emergency, and that requires additional sighting. Okay, so for less helium, the less sighting issues there That's just an example of this. So this is actually quite a, there's actually two extremes in MR. On the one side, people are building bigger magnets, not only field strength, but also the radius of the magnets has been getting bigger, because for clinical cases, not only are people getting bigger, but also, if you have someone who, has been in a car accident or something, and it's just nicer to have more space, in case you have to arrange them in a certain way. But on the other side, there is a trend towards low cost portable magnets. And this is certainly, when you think about projects, this is sort of very interesting area to look at is, what if you want to go to the other end? What if you want to bring MRI to developing countries, where there's not the infrastructure? What if you want to have an MRI at Walgreens or Walmart or whatever? What you want to have MRIs everywhere, right? So this is the first commercial thing out there. It's by a company called Hyperfine. This is a 64 millitesla magnet, so quite a lower field strength. This is them sort of putting a baby in the magnet, and this is a case where they drive around in a van and they scan people with this. Okay, so this uses has lower field strength, so it'll have less signal, and they make up for a lot of that using deep learning and AI to sort of reduce the noise. And so we'll talk a little bit about that later in the course of how you can trade off signal, but then if your reconstruction is smarter and you can use better use of deep learning, then you might be able to get some of that back. Okay. Cooley was a PhD student at MIT, and now a scientist there who's did this magnet here, which is sort of a permanent magnet, and then gradient coils and RF coil. So you can sort of see it's very small. And here they just use permanent magnets so that it's just sort of like metal, you sort of niobium, I forget what it is, but it's basically, you just have magnetic material and you form it in a way. So you don't actually have to run any current through it. It's that magnet is always on, just like a refrigerator magnet. The cost of this commercially is they're trying to sell it for about $50,000, so much less than, and then there's going to be some subscription service, I think, to sort of keep charging you. And then this is just a startup that some colleagues started. And here their plan is to build magnets that are, the whole suite could be within like a shipping container. And then this could be shipped around to all parts of the world and have lower cost. And okay.
Do you have all the MRIs in
Yes, those are, okay, so there are things called trailers. So you can buy an MRI in a trailer. So like if you don't have a building, you can actually buy a trailer from a vendor, and that will come and you can site it in your parking lot. At some point that, in general, those are typically don't work as well because they're not as stable and everything like that. And also, but it's often a temporary measure until you can build a building. Okay. It's also good if you're not sure you want it. Typically you would lease it as well, right? Just the way you lease a car, you can lease a magnet. Okay. This is another example of a low field magnet, I think from Italy. So you can sort of see there, they're building also with, this is 72 millitesla magnets are quite low. And you can sort of see here, you can use it outside or at the house. And this is an example of the images you get from the magnet. And then if you do some image processing, you can do a little better job. And what you're seeing here are these sort of implants here. This person had some surgery here. And the comparison is with a commercial 3 Tesla magnet. Okay. So you can sort of see it's a little noisier, but it's not too bad, right? I mean, if depending on what you need it for. And so the interest here is like, not everyone needs the highest end imaging. And so are there applications where having sort of slightly lower quality images is sufficient for what you need to do? So that's an interesting thing to think about. Okay, so we spent quite a lot of time on the magnet itself, which tends to be the most expensive part of a system. The next thing we're going to talk, so we talked about this part here, sort of the main coil, and then I think we're going to talk about the RF next, and then also the gradient coils. Okay. Okay, so the RF coil is pretty simple, actually. I mean, it's typically just made up of a bunch of copper wires arranged in a way that will create a magnetic field. and try to introduce some terminology here. The main field, we're always going to call that B0 or the B0 field. Okay. And the RF field by convention is called the B1 field. All right. And the B0 field, in this case, is pointing along, and by convention, we'll typically call this the Z direction. Okay. And the B1 field to be effective, we typically want to have it, the effective part is the part that's perpendicular to the B0 field. Okay. So typically we'll want, if we have a magnet with a B0 field, oh, let me just stop this poll. Hold on. I'll get rid of these polls. All right, well, let's just keep going. So if you have a magnet with the Z direction here, then typically you want the B1 field to be pointing perpendicular to that. And so you can, the simplest coil is actually just a loop, okay? Because this will create a B1 field, and if you point the loop in this direction, then the B1 field goes this way, right? And the more complicated ones we'll talk about, you'll manipulate the magnetic field in certain ways. So as we talked about before, you could have an RF coil. In this case, it's just being called the transmit coil. All major whole body systems have what's called a body coil. So this is a coil that's big and goes around the whole body, and it can both transmit and receive. Okay, but there has been over the last 20 years, especially, sort of a trend to use one coil for transmit and then use a lot of smaller coils to receive. Okay, there's two advantages of that. One, you're putting the coil closer to the body, and so you can get more sensitivity. The other advantage we'll see later in this course is it allows you to go a lot faster, and it allows you to do really interesting reconstructions, and especially with deep learning, you can start doing things that you could never. I mean, right now people are doing things that they didn't think were possible 10 years ago because of deep learning. Okay, so these are some examples of coils. So there's lots of different geometries and designs that people have used over the years. These are just showing some more examples, but you can sort of see these are the types of coils that you could easily build, by yourself. I mean, it's the simplest thing is just a loop coil with like a capacitor and a few things. Okay. More complicated things that you might get from a manufacturer. For example, this is an array coil with lots of different coils that covers the whole body. Okay. So for example, if you wanted to do something a little more CT-like, where you do a whole body scan, then this is the coil you could use. This is a coil that's basically, this has 32 of these loops shaped in sort of a soccer ball design. This was the original prototype built at Harvard MGH, and then they were working with Siemens, and so this eventually became this. Okay, so initial engineering, and then after a lot of development, it became this, which is now, for example, we have one of these coils over at our center. Okay, the next coil we're going to talk about are the gradient coils. All right, and there will typically be 3 of these. Okay, there's going to be an X gradient coil, a Y gradient coil, and a Z gradient coil. All right. And this is an example, I think, from the Siemens factory floor. You can sort of see these coils have very interesting patterns. Okay, and right now they're all computer designed to sort of optimize their performance. The basic idea is there's a Z coil here, which is just 2 rings here. The most simple version you could have is 2 rings. This is going to create a varying field in this direction. Okay, these X coils are going to create a varying field in the X direction, and the Y coils would create a varying field in the Y direction. So we're not going to go too much into how this works, but that's certainly an area that people could do a project on if they wanted to get more into gradient coil design and talk about how these are designed. The basic idea is what you want is that you have the main field, the B0 field, okay, which is pointing in the Z direction. And these gradients, we're talking about gradients in that BZ field. Okay, so we're still talking about the BZ field, but now we're just talking about how that BZ field varies either in the X direction, the Y direction, or the Z direction. And so we'll give these special names that are used so often. We'll call this G sub X, G sub Y, G sub Z, which is the gradient in the X, Y, and Z direction. All right. So, get used to the term B0, that's the main field, and get used to seeing GX, GY, and GZ, because those are the gradients. Okay. So for example, if I have GZ greater than 0, I'm looking at the Z component, right? So I'm still looking at the Z, and assume Z is going in this direction. I'm still looking at the Z component. And let's say Y is going, Z is going in this way. So if G sub Z is greater than 0, it just means as I move along the Z direction, that field gets stronger. Okay, but it's the BZ field that's getting stronger. If I have GY greater than 0, then as I move along in the Y direction, the field's getting stronger, but it's still the BZ component I'm talking about. So that's what the gradient, and we'll talk a little bit about why you need gradients when we make imaging. Today, we're just giving you an overview of all the different components. All right. These are just simple examples showing that like you have two coils with current going in opposite directions. You can create a variation in the B field such that it's positive gradient, more positive as you go this way in Z and more negative as you go this way in Z. Okay. Also, this is a great website, MRIquestions.com. This is a retired great professor of radiology who just spends his time like working on this website. This is usually one of the best first places to go if you want to understand something about MR. Okay. It certainly wasn't around when I started learning MR, and it's just a great resource. Okay, so if you're looking for things or have additional questions, certainly you can ask us, but also that's just a great website to know about. Okay, so more sort of fancy coils than are look like this, where you can see this is obviously computer designed and sort of gets you. And the whole idea is they're designing them to be as linear as possible within some regime. Because we'll find out later that's if you have things that are linear, then you can actually implement the Fourier transform of your object. Okay. If they're nonlinear, you can still do it. And today with deep learning, it's actually easier. But 10 years ago, it just involved a lot more math to do it. Okay. Okay. So these gradients, we'll see later. We switch them on and off a lot. Okay. So basically, as we're trying to go get data in Fourier space, we need to change the gradients. And so these are actually going to be playing out typically at audio frequencies. Okay. And so if you're ever in an MRI system, you'll hear that it's at least most of them are fairly noisy. Okay. Now the manufacturers are working on making them less noisy, but up to now they are fairly noisy. And the part of the reason is because these gradients are switching off at the audio frequency, right? With a lot of power. So for example, typically, most high-end scanners like the ones we have, it'll be like a 1 megawatt gradient amplifier. Okay. And so by comparison, I think the audio amplifiers I used in the Metallica 2017 tour in the stadium was only 367,000 kilowatts, which is less than this, right? So that means if for whatever reason you had an MRI system and decided you didn't need it anymore, you could take your amplifiers and go to a stadium and like do a rock concert. Okay. So this is what sort of things look like. You'll typically have the magnet in a magnet room, and that's a shielded room. Okay. So it'll have both copper shielding and probably some iron shielding. And then the person sits out here in the console room and operates the magnet. And typically, in a lot of cases, we'll have a camera so we can sort of see what's going on inside as well. And so here we have the magnet, and then all around here, there's a lot of things. So for example, we have things that control the transmit power and also receive the signal. We have things that program the gradient. We have things that store the data, that process the data. And this thing here is very important, the pulse sequence program measurement and control. Basically, this allows you to control both the radio frequency and the gradient pulses. And as Professor McVeigh mentioned, MRI is a very academic endeavor. It was developed in academia, and still, like if you go to the MRI conference, it's like 5,000 people doing research in MR, whereas I think the CD conference is much less. And that's because very early on, the manufacturers decided to just open up their software environments to the academic researchers. And so, for example, here at UCSD, we have full access to GE and Siemens, and maybe even Canon. So we can actually go in and create our own programs that manipulate the way the gradients in RF are played out. In fact, one of your TAs, Ryan Barnes, has sort of been doing that for some of his research. So if you want more information on that, you can certainly ask him what that's like. but it's sort of cool. You get to sort of control this, $2 or $3 million machine, and it does whatever you tell it to do. The other interesting thing is that people are, there is a big push, especially as people are playing around with these low field magnets, to have open source. So this is, you can go online, if you download this paper, it'll have links to some open source websites where you can actually download code and circuit diagrams and build your own MRI system using off the shelf. In this case, they're using a Red Pitaya SDR lab. Has anyone used that? I'm not familiar with that, but it's sort of like, I imagine it's sort of like Arduino on steroids. Okay. So anyways, there's a community. If you're sort of a hardware person, you could actually build one of these pretty easily now, because there's a community that will help you build your own MRI system. But you can sort of see the basic idea is still the same. You have to have something that controls transmit and receive. You have to have something that controls your gradients. And so this ADC is analog to digital converter. So the signal is coming back and the DAC is sending the signal out. Okay. And so it's just a lot of control of these signals. Okay. So that's really the overview of the system. So now we're going to start talking about what the different parts of the system do. So before I go on, are there any questions at this point? Okay. So there's, in this course at least, we're going to talk about we're going to break MRI into sort of 4 main things that the system has to do. The first one is polarization. Okay. First, we have to create some magnetization to use. Okay. And that's the job of the big magnet. The big magnet's job is to create some polarization. Okay. The next job is the RF coil, and it has to do what's called transmit. And this is something, that function is called excitation. We're going to have some magnetization, and then we're going to excite it. Okay. We're going to put some energy into the system, into our sample. The next thing is called encoding. Okay. This is where the imaging happens, and that's the job of the grading coils. And what that does is it'll take, we'll talk about spins in a minute, but it will take the protons in your body and it will manipulate them in a certain way that allows us to make an image. And the last step is integration. And this is the job of the RF coil on receive. So the RF coil has 2 roles, both transmit and receive. The RF coil basically integrates the signal from all the parts of your body. And so that's, instead of doing an integral in MATLAB, you're just using the RF coil to do an integral for you. Okay. So the cool thing is all these things together actually do the Fourier transform of your object. Okay. But not in MATLAB, they do it with just electronics and physics. Right. Okay. And the other thing about MRI is it's got a very flexible contrast. So for example, this is the same brain, and just by manipulating the timing of parameters, you can make the same brain look very different. So you can accentuate, in this case, the gray stuff here is gray matter, the white stuff here is white matter, and this black stuff is cerebral spinal fluid. So those are the 3 main tissue types in your brain. And in this case, I've made the fluid very dark, but in other cases, you might want to make it very bright. For example, tumors often have a lot of CSF in them. And so you might, if you want to make a tumor bright, you might choose this setting. Okay. The other thing you can do with MR, and this is also possible without contrast, although you can use contrast, is you can create these exquisite angiograms and look at the vasculature in the brain. This is actually looking at the veins because the veins have iron in them, so you can actually make a nice image of the veins. This is something we'll talk about sort of towards the end of the class. This is actually what's called diffusion tensor imaging, and essentially, and this is still remarkable every time I look at this. What this is showing you is this is the wiring diagram of this person's brain. Okay, showing all the major wires of their white matter fibers in the brain. So basically, your brain you can think of as a bunch of processors in your cortex. So all your processors are around here in your cortex, and all this white stuff, that's just like the wiring connecting different parts of your brain. And so this means I can just put any of you in a scanner for about 10 minutes and map the wiring in your brain without any contrast. You can go in and come out and you won't have felt anything, all right? And the last thing in the area that I really focus on is fMRI, where not only can we map the wiring and structure of your brain, but we can also see what your brain is doing in real time. Okay, so as you're sitting here listening to this lecture, you know, your blood flow and oxygenation levels are varying all the time in different ways. And so we can actually measure that with MRI now. Okay, okay, so now we're going to switch gears a little bit. So we'll talk about those applications towards the end of the course, but now we're going to go back and for the remaining, I guess, 25 minutes, we're going to talk about spin and get to precession and polarization. Okay. So some of you may have heard about spin. So it's intrinsic angular momentum of elementary particles. So electrons, protons, and neutrons have it. In this course, we're going to focus on protons. Okay. And there are a lot. The good thing is there's a lot of protons in your body, especially hydrogen protons. And so in particular, we're going to focus on hydrogen protons. Spin is quantized, and so really to go into spin, you do need quantum mechanics, but we're going to sort of ignore all of quantum mechanics in this course and just do a classical view. All right. So this isn't really how things work, but it's a useful picture. So imagine a proton, right? You can model it as like a charged sphere, right? It's a positive sphere, okay? And if it has angular momentum, then it's rotating around its own axis, right? Okay. So if I have a sphere with charge, it's rotating around its own axis. What else does it have? Okay, if I have a sphere of charge and I just spun it around, what is that equivalent to? You've got charge moving around. What do we call that? In EM, anytime you have charge moving around. It starts with a C, current. Okay, so it's current, right? So if I just had a charge and I moved it around like that, that's electric current, right? So electric current, if you go back to Maxwell's equations, if I have any current or Faraday's law, just it creates a magnetic field. Okay. So anytime I have something that's charged that has angular momentum, it's going to create a magnetic field. Okay. So that becomes very important. So right now, as you're sitting here in this room, you all have hydrogen protons in you, right? You can safely assume that. And so all those hydrogen protons have spin in them. So there is this sort of intrinsic angular momentum within you. And there's also lots of little magnetism in you. You have lots of, many, many magnets in you right now, just sitting there. Okay, so as I said before, we're going to focus on hydrogen proton, which has spin of a half. Now, it is possible to MR with other things such as carbon-13, fluorine, sodium, phosphorus, even oxygen-17. But these tend to be specialty things. They are done sometimes clinically, but by far most scans are done with hydrogen. Part of the reason for that is these don't have very much abundance. Okay, there's very little signal there. So it's just harder to get images and good data from those other protons. So typically, most clinical MRI we're talking about hydrogen proton. Okay. Okay, so as we talked about before, anytime you have a current, right, you're going to have a magnetic field created. And so we call that a magnetic moment. So I just had a loop of wire with a current I and some radius A. It has a magnetic moment U, which is proportional to the current, the area, and N hat just represents the direction that's pointing in. Okay. So we're going to talk a little bit about maximum energy states. So if I have a loop of wire, it's going to have a little magnet field like that. And now we put in the presence of another field, a bigger field, or any field, then it turns out that the lowest energy state for this guy is when this field is aligned with this field. Okay. And then the maximum energy state is this one, because it's going to take work for me to sort of work against that main field and turn it on its pointing the opposite direction. So there's going to be a range of energies depending on which way the magnet is pointing in. Okay. And so right now we're all sitting in the Earth's magnetic field. Okay. And so that's already creating some energy difference. So the protons in your body are in a low energy state when they're aligned with the Earth's field here. I don't know which direction it's pointing in, but probably pointing like this direction or something. There's some inclination and declination of the field here in San Diego. And it's also, so that means that the spins are going to have some preferred orientation even right now in your body. And so what that means is that anytime you have sort of a distribution of energies, things tend to follow what's called the Boltzmann distribution. Okay. So the best, one of my sort of favorite analogies of this is if you think about a parking garage, like Gilman parking structure or whatever, you basically, it's got, I don't know how, it was like 5 floors, right? And so assuming there's no A, B, or S permits, you just park anywhere you want. Well, typically you're going to find the bottom floors are the most occupied, right? Most people are just going to go and park in the first parking spot they want. But maybe you had a lot of caffeine in the morning, or you're just really peppy and you want to do something, you might go up a little higher, right? You have a little more energy. And so you typically find an exponential distribution of cars in a parking lot, right? There's always going to be someone who wants to park on top, right? For whatever reason, but not that many, right? Most people will just go as far as they can go and just park there. Okay. So what you're going to find is if you look at the number of spins, that most of them, the distribution is there's going to be more that are aligned with the field and less that are anti-aligned. And then in between, it's an exponential decay, right, or distribution. So what that leads to is the first important concept we have, which is polarization. And this is what we're terming the equilibrium magnetization. So these are the spins in the absence of any field, okay? And so here there's no preferred energy. And so if I thought about taking all these spins and these are little arrows and putting them, such that their tails are at 0, since they're all pointing in different directions, the vector sum of that's going to be 0, right? There's going to be 0 net magnetization, right? But now, if I think about all these little vectors, and so most of them, tend to want to point along the field. So now if I think about taking all these vectors, putting their tails here, and taking the vector sum, I'm going to get some net magnetization, okay? And so that net magnetization is given by this formula, and an important part is it's proportional to the B field. Okay, so that's one step in explaining why people want bigger and bigger magnets, is because the bigger that B is, the more magnetization I have to deal with. I essentially have, per unit volume, more magnetization that I can manipulate and use to make my image. Yes? Yeah, sorry, that should be B0. Yeah, the main magnetic field. Good question. Okay. And then I think the other thing we're going to talk about is torque. And then this is going to lead to something called precession. Okay. So if I have torque, just means this. If I have like a, let's say I have a magnetic field pointing this way, right? And then I point the spin. So the spin is very happy to be aligned here, right? That's a low energy state. But now let's say I put energy into the system and I go like this, right? So now if I'm away from equilibrium, there's going to be some desire for this to come back, right? Okay. So that's sort of just, if this has no angular momentum, then torque is very simple. If I go from here to here, it's just going to, the torque is just going to try to, the thing is just going to go back to here, okay? And so similar to a compass needle, right? If I have a compass needle, it points along the Earth's magnetic field. If I move it away, it will just try to go back, okay? So that's sort of what the system will do. But now what we want to think about is, what if this is not just a compass needle, but what if it's rotating around its own axis? And then it turns out things are very different. The physics becomes very different. And that's what we have with torque, okay? So we can work through the math, but it's actually better to just sort of do a demonstration. So let me get up and let's see. Okay, so I have this wheel, which I always have to take off my bike once a year to do this demonstration, or at least once a year. Okay, so this is going to go through the main concepts that we want to get across. So first of all, would you all agree that this is the lowest energy state of this wheel in this configuration? So what is the highest energy state? How could I put this in the highest energy state? Here, right? That requires the most work, right? And then where will it go if I let go? It'll go back to the lowest energy state, right? So that's that, right? And if I put in half of that, I put in this much work, it's sort of at a medium energy state, and it's going to go back to the lowest energy state. Okay, so that's no torque. So there's really not anything too interesting about that, right? But now, as anyone who has ridden a bike knows, if I says any momentum, it's actually now processing. So it's not, you see, it's not going back to that state, right? It's just, and as long as there's no friction here, it's just going to keep going forever, right? So this is like, whoops, the gyroscope, okay? So this is essentially the picture you want to have in mind when you're thinking about spins, okay? In fact, one way you can think about it is, we draw these little arrows for spins, right? And so, for example, if you think about this has a magnetization this way, that's pointing the same direction as gravity, right? To the slowest energy state, right? If I take this spin and move it here, right? Now the magnetization is pointing this way, right? And this is sort of a medium energy state. And then I spin it, that magnetization is now going around, and that's precession. And this is what we make of use of in MRI. And it turns out that the rate at which this precesses, okay, is actually going to depend on, if I could vary the gravitational field here, I can make this precess at different rates. Okay. So in the magnet, we do that with the gradients. Okay. So that rate of precession is going to depend on the local magnetic field. Question?
When you're in the lowest state,
Yes.
like those protons like spin, or they just stay still?
They still have, they're like this. They still have angular momentum.
Always like spin.
Yeah, there's always angular momentum is intrinsic. So they always have angular momentum. So the main thing is just what is the direction of what direction are they pointing in? So this is what leads to precession. And so the main thing is that the frequency at which they precess is known as the Larmor frequency. And this is given by omega equals gamma times B, where this is B0. Okay. And for now, it's B0. Later on, it's going to be B0 plus some delta B that we add. Okay, when we add the gradients. Okay. And this gamma is known as the gyromagnetic ratio. Okay. So yeah, I mean, you can go online and look at lots of videos of people spinning bicycle wheels, but I did it, so you don't have to do that, right? Okay. All right, so now let's talk a little bit about notation again. So remember we said 1 Tesla equals 10,000 Gauss. The Earth's field is about half a Gauss. And now let's look at, for hydrogen, we have hydrogen proton gamma is 26,752 radians per second per Gauss. Or if we want to convert that into Hertz, so we divide radians by 2 pi, Hertz is cycles per second. Okay, so how many rotations you do per second. This turns out to be 42.58 megahertz per Tesla. Okay, and if you're an MR, you just sort of memorize this, right? That's like you see this number all the time. So that's over time, you just say, okay. So that means if I have a 1 Tesla magnet, if I put you in the 1 Tesla magnet, all the spins are going 42 million times per second. Okay, if I put you in a 3 Tesla magnet, they're going around 127 million times per second around their own axis. Okay. And I put in your Earth's magnetic field, well, I'll let you calculate that for the homework. Okay, I think something like that's on the homework. These are just some talking about different nuclei, and once again, we're going to focus on hydrogen proton. This is the gyromagnetic ratio, and the other thing here is the abundance. You have like 88 molar, whereas these are like in the millimolar range. Okay, so the relative sensitivity drops a lot. Okay, so let's talk a little bit about the Larmor frequency. So we can think of it in terms of either the radians per second or hertz per second. Okay, and then there's just a 2 pi relationship between those. So if you had a 1.5 Tesla system, then the frequency is about 63.86 megahertz. And so that puts you pretty close to the FM radio band, right? So for example, KPDS transmits at 89.5 megahertz. this is just saying that, reminding you that Earth's magnetic field is 50 microtesla. So a 1.5 Tesla system is 30,000 times stronger than the Earth's magnetic field. Okay. And the 3 Tesla system will be 60,000 times stronger. And so a 3 Tesla system, that puts us here in the civil aviation band. Okay, so that's basically, there's broadcasting all the time for the airplanes, right? Air traffic control. And that's why we have to have a shielded room, right? Because otherwise our image is going to be contaminated by like air traffic control, okay, which is not what we want. And in your homework 4, you're asked to, and if you also look at the supplementary session, there are cases where you sort of see, like you're asked, what happens if there's like a spike of energy in the RF, in the Fourier domain, what happens to the image? That actually happens in real life. When anytime there's like a spark of energy, either from the outside or even just something happening in the room, like 2 pieces of metal touching each other, that can give a spark of RF energy. And if the RF coils pick that up, that appears as a spike in K space. Okay, so in your exercise, you're actually simulating what happens and getting some sense of why you have to have a shielded room, because you don't want random bits of energy coming into your Fourier transform. Okay. Okay, so we talked a little bit about the magnetization of a given spin or a collection of spins. And so typically, when we talk about imaging, we're not just talking about just one spin. We're always talking about how many spins are in a voxel or in a certain volume. And it might be like a 1 millimeter qubit volume. And therefore, the magnetization is just the net sum of all the protons in a volume. Okay. And so that's given by this picture. So in a given volume, you have to look at all the different spin orientations, and it's the net magnetization that we care about. And this is the equation of motion. So basically, dm dt equals gamma m cross b. Okay, and actually, I'm going to go back to that picture here. So for a single spin, d mu dt equals mu cross gamma b. Okay, so let's talk about what that looks like. So basically, just to remind you what the cross product is, that just means if I have my B field this way, right, and this is my spin, right, okay? So mu cross B, you use the right-hand rule, right? So the mu cross B is going to point this way. So it's going to point perpendicular, it's going to point in this direction. So that's saying that the change in this mu is going to be perpendicular that way, and that's what makes it go around. Okay, at every point in time, this d mu dt is saying you're going to go this way, perpendicular. Okay. If you're going to look at this from up top, for example, then that's always going to be tangential, right? That d mu dt, right? So it's going to make you go around. Okay. Question? This one?
Yeah.
Yeah.
So here you said, I think one of the things that you said, like as you increase the magnetic field, it's proportional to the number of spins.
Yes.
So as you get more spins, does that mean the number of photons are increasing?
Yeah, so that's the other thing. So, right, so that's where there's a trade-off between like, we'll talk about this a little later, but when you do an MRI, or especially an MRI, one of the things you have to pick is what resolution you want to scan at. Right? Do I want really high resolution? Do I want like 1 millimeter voxels? But then the problem is each voxel has less spins in it, right? So it's going to be noisier, right? So and it's also going to, as we're going to find out, it's going to take longer as well. Okay. So there's a trade-off. You typically want to go to the resolution that you really want. And so, for example, if really what I care about is 3 millimeter voxels, then it's actually advantageous to go to that, and I get more signal, and there's less. I can go faster too. So yeah, the number of protons is proportional to the volume.
So if you increase the number of protons per volume, would that start to, as you increase the number of protons, would that start to distort the signal because the protons are also like opposing each other?
That's a great question. So we'll talk about that when we get to relaxation. So these protons are always interacting with each other. They're essentially little magnets, right? So yeah, I mean, there's not really an easy way to increase density right in the body of someone, but you can have things, for example, we'll talk about later, where, for example, as your, the amount of blood you have in a certain area can affect the field and distort the field depending on what it's doing. So we'll get to that later in the course, but that's a good thing. That the sort of preview where we're going is that we're talking about protons in your body, and they not only act according to the magnetic field, but they also interact with each other. Okay, so the last concept we're going to just introduce you today is RF excitation. Okay, so this is the basic thing here is we've created this magnetization. Okay, and now the thing is, yeah, we could detect the magnetization, here and try to measure the magnet, but it's like sort of measuring the magnetic field of this thing here, which is just not that easy to do. That's called like direct detection of magnetization, right? What's a little easier to do electronically is if I can make this magnetization tip it away, then it's going to go like this, and it's going to create it's going to create a varying magnetic field, right? Which creates something that I can, if I have a loop out here, that's going to create an electric field that I can now measure easily. So creating time varying magnetic fields is part of the detection process, okay? So that's sort of like letting me broadcast sort of my signal. Okay? So that's why we want excitation. We want somehow to take this magnetization, tip it away, so now it can process. And then it makes it easier for me to measure somewhere else. Okay. So that's the process of RF excitation. And so I think this is a movie, sort of shows, so all the spins are processing, and they're all processing, and then we're just trying to tip that whole population away from the main field. Okay. And that's the process of excitation. Let's see. Okay, so yeah, so excitation, and so the key point that we'll find out is the way we do that is, here's the main field B0, and the way we excite things is with this B1 field, which in this case is pointing perpendicular to the B0 field. Okay. So we're going to end with sort of a thought experiment. Two thought experiments to think about. One is, I don't know why this person has this car in their backyard, but they do. Okay, it's on a swing, right? And so this car maybe weighs, I don't know, 2 tons, right? So let's say I say you can come up with your pinky finger, and your goal, I'll give you like, I don't know, $1,000 if you can set this car swinging in the next minute, right? And it has to go like 1 foot in either direction. So think about how you would do that, okay? The other thought experiment I want you to think about is, imagine this is a merry-go-round. So you see these at carnivals, and there's one at Balboa Park too, if you ever want to go there. So imagine this is your friend here, and she's sitting on a horse, and she's going around on the merry-go-round, right? And you attach a very thin thread to her. And also, I'm going to give you $1,000 if you can somehow manage to pull her off the horse in the next minute. Okay? So go ahead, and you have give me 1 minute to talk with your neighbors, and then we'll reconvene and see what people think. Yeah. I'm not actually to give you $1,000, sorry. I just imagine, or it's $1 million. It's like Mr. Beast would give you money. I'm not going to give you money. Okay, we have about another minute, so let's see what people think. So anyone, for the merry-go-round, what should you do? You have a thread, you want to pull your friend off the merry-go-round. So what do you need to do? And it's a very thin thread, so if you pull too hard, it's going to break, right? So what's your only chance of getting her off the merry-go-round? Sorry, go ahead. Any ideas? Okay, use psychology. Okay, let's say you can all use physics. Okay, yes.
Well, if this person's on the edge of the circle, then
Yeah.
just pull in a direction that kind of follows the rotation.
Right, you've got to run along with her, right?
Yeah.
So if I'm running along, I have to go this, and you have to go the same speed as the merry-go-round. Yeah, exactly. Well, actually normal. Yeah, so you've actually always pulling in a normal direction, right? And you got to run along with her. And you're just applying a very faint force. And if you do that and you're at the right speed, she will come off, right? Okay. What about this big car that you want to poke with your pinky finger? You don't want to break your pinky finger, right? Your pinky finger is not very strong. So what do you do with your pinky finger? How? Yeah, exactly. Yeah. So has anyone ever pushed anyone on a swing? Yeah. So you know the answer, right? Basically, if you push at the wrong time, you're gonna break your pinky finger, right? So you better push at the right time, right? I mean, the stakes are just higher, but if you push a kid, it's easy. You screw up, it doesn't matter. But if you push like a 300-pound guy and you screw up, then you might get, bowled over. Okay. So last thing I'm going to end with is just that is the basic idea behind RF excitation. Okay. So I'm going to play this movie and then we'll review this next time in 2 weeks. So basically, if I apply that cyan thing is the B1 field going around at the same rate that the spin is precessing. And if it's at the right frequency, it will cause that spin to precess down. If I go at the wrong rate, it's sort of like trying to push that car. It's just not going to move. The spin's going to stay up there. Okay. All right. So I think that's it for today. So I will hang around if there's questions for office hours. Otherwise, we'll see you guys next week for projects.
Yeah, grad student researchers and today is the strike authorization vote. I got an email vote. Yeah, I'm gonna go. Yeah,